would like to thank the organizers for inviting me here to present this work. We are shifting gears. We were talking about how to save the euro crisis, and this is more of a technical paper about how to evaluate forecast densities. It's still a practical and interesting topic, but still very different in focus. So this is joint work with Tatevic, that was a student of mine, and we have a series of works on evaluating forecast methodologies, and this is one of the techniques that we have come up building on that series of works. Can you all hear me also in the back? Yes? Okay. Okay, so first I should probably talk about what we are trying to do here. We are trying to evaluate how good the predictive densities are or forecast densities are, and we will propose new techniques to evaluate whether these predictive densities are correctly specified, are good. And first I would probably try to argue why we care about the forecast densities. If you have never dealt with the topic, you might think it's not very important, but indeed it is. So why density forecast? So typically you would be used to know a lot about the point forecast, right? So what is your best forecast of inflation 1 year from now? Right, forecast densities are a broader concept. They measure the uncertainty around that point forecast. Okay, so sometimes it is not enough for you to know that the best forecast for tomorrow is sunny, right? You would like to know how certain the forecasters are about the fact that it's going to be sunny. Are these guys really pretty sure about the fact that it's going to be sunny? Or maybe it's a wild guess, and you would like to take that information into account in your own decision process. So this is what the forecast densities do. They will give you information about the uncertainty around the point forecast. Going back to economics, central banks have been very interested in forecast densities to try and communicate to the public the uncertainty around their point forecast. This is an example from Bank of Canada, where my co-author was working at. And this was a picture taken from 2012. This is a plot of the path of inflation in Canada up until 2012. This is the realized inflation. And this is the path of inflation for the next couple of years. So this is the median point forecast of the Bank of Canada. Inflation would have been around 2% in the next couple of years. And the gray bands are measuring the uncertainty around that point forecast. So you can think about predictive, these bands coming from predictive densities. So you can think about, for example, a prediction for 2014, thinking about a predictive density, maybe a normal distribution. These are symmetric bands. So you can think of a predictive density like a normal distribution coming out of this picture. And then these would be quantiles of that normal distribution. This would be 90% quantiles or 50% quantiles. Right? So our job here is to evaluate how good these predictive densities are. We will not focus on, in our empirical application, on the Bank of Canada to avoid the problems with Tatevic being an employee of Bank of Canada. We will have applications to other empirical analysis. But that's what we set up to do. So our job will be to say, look, you give me a predictive density or a forecast density, and I would like to evaluate whether you're doing a good job. Is this correctly specified? And what we do is that we take a step forward from the existing tests, which test for the correct specification of these forecast densities, focusing on a null hypothesis that is based on a pseudo-true parameter value. So all of this will become clear if you're patient enough. But what this means is that when you produce a predictive density, you are typically using estimated parameters from a model. And then when you evaluate this predictive density, the null will be on the pseudo-true parameter value, which is the value of the parameter if you had a long enough sample so that it will converge to some population value. So we do not do this. We change the perspective, and we instead evaluate predictive density at the estimated parameter value, because we argue that this is what really people care about. They want to evaluate the forecasting ability of their models at the estimated parameter value. This is what they want to evaluate. I will try to argue that this is a good strategy. And it also gives you some interesting tests or easy to use tests. And then we will apply our techniques to evaluate the survey of professional forecasters' predictive densities. This is a very interesting data set collected by the Philadelphia Fed. They collect information from survey participants about what the predicted values of inflation will be, the actual predictive distribution of that. So for example, if each one of you were a forecaster, I would ask you, what is the probability, what do you think is going to be the probability that inflation will be between 0 and 1%? What is the probability that inflation will be between 2 and 3%? So each one of you will give me this histogram, and we will evaluate whether on average these guys are right. And the second empirical application is more geared towards economics. We will take a dynamic stochastic general equilibrium model that is typically used nowadays in central banks. From there you can get a predictive density, and we will evaluate whether these are good predictive densities or not. Okay. So what I plan to do is, I'm thinking that maybe not all of you are familiar with predictive densities. So I was planning to spend quite a bit of time on a review of the literature where all of us can learn. And then I will tell you a little bit about how we propose to change the tests. I will skip the Monte Carlo. These are typical tables where we show that we are right? So you can take a look at the table and learn from there. And then I will tell you a little bit about the empirical applications, what we learn about how forecasters are doing. So here is an example. So thinking about the review of the literature, I would like to define what a forecast density is and how it can be constructed. So here is a little example of how you can think about forecast densities. So I will take a simple example from a Stock-Watson type of analysis. They are interested in forecasting a quarterly inflation, H periods into the future. For me, H will be given. Okay? And what they do is that they say, well, inflation, H period in the future can be modeled as a function of past inflation, a bunch of legs of past inflation, and a bunch of legs of an additional explanatory variable. They take the variables one at a time. You can think of X being, for example, unemployment in terms of a Phillips curve. Okay? So this is a typical model you will find in this literature. And if you're interested in point forecasts, that's all you need. You estimate these parameters, and then your point forecast of the future change in inflation will be exactly this, the conditional mean. Okay? So this is not enough for me. I would like to have a measure of uncertainty around this point forecast. And an easy way of obtaining that is by a density forecast, and you can obtain that by simply making assumptions on the distribution of the errors. Okay? So for example, if you imagine that with the same model now the error terms, you're assuming that they are normally distributed with mean zero and variance sigma square. The particular assumption of normality is not important. We can allow for many types of distributions. This is just an example. Then you can estimate these parameters, right? The same as you've done before. You can now also estimate the variance of the error term, for example, with the sample variance of the fitted errors. Okay? We suggest you do this rollingly over time, and this will be important for us. Okay? So this is, if you will, the interesting part as well as the limitation of our approach. This has to be done in rolling windows. So the idea is that at some point in time, you will start your forecasting procedure. You will obtain one density forecast. Then you will re-estimate the parameters as new data come in. You will re-estimate the parameters in a rolling window of a fixed size using only always the last R observations. Okay? So as you move through time, you will re-estimate the parameters in a window of R observations and produce a sequence of density forecasts. So this sequence I will denote phi hat, right? So if the errors are normal, then the y will be normal as well, with the mean, conditional mean, which is this. That's my conditional mean, and the variance, that is the variance of the error term. Okay? So that's it. That's your density forecast, and you will have a sequence of them over this, over a period of, let's say, p observations. Okay? So this is my sequence of density forecasts. So my job will be to evaluate whether these guys have done a good job or not. And so the issue in the literature is the following. You have a density forecast. Imagine you have, maybe this is your, so now it becomes a bit complicated. Okay. So imagine you have your density forecast, it's a normal, right? At each point in time, you have your predictive density, and then you have to compare it with a realized value, but you don't have a predictive density realized value, right? You have only maybe one observation, so maybe this is your realized value. So how do we compare a sequence of predictive densities with a sequence of predicted values? Okay? How do we learn from the data whether these predictive density are correctly specified? So one way to do that was suggested by Diebold, Gunther, and Tai. It's not the only way of doing this. There are other techniques, but we will take this approach, and it's called a probability integral transform, or PIT for short. Okay? So the PIT is the cumulative density function of your forecast density at the realized value. So that sounds a little bit complicated, but what it is, it's simply this. This is your realized value, right? And so what you're doing is you're calculating the area under your predictive density up until your realized value, okay? So this is what the PIT is. That's the PIT, and this is, I will call it the ZT plus H. Okay, so that's my PIT measure. And the beautiful result in this literature, so this is the formula, the beautiful result in the literature is that when the forecast density is correctly specified, the PITs are uniform, independent, and identically distributed. Okay? So just to give you some intuition about what why this result holds. So the PIT, we said, is the integral of the predictive density up to the realization. Okay, so it's this area over here. And so why is it uniform when the forecasting density is correctly specified? Well, this is an integral of a predictive density, so the integral can be anywhere between 0 and 1, but it's going to be between 0 and 1, right? So if your forecast density is correctly specified, then you should observe realizations that are sort of randomly between here, here, and here, so they happen randomly in the space where your density is defined, right? So then the integral will be between 0 and 1, but will achieve values that are between 0 and 1 in a random way. So what is the distribution that is distributed between 0 and 1 randomly with equal probability? Well, that's the uniform distribution, right? So that's why when predictive densities are correctly specified, then this integral should take values between 0 and 1 in a very random fashion, okay? So if we want to evaluate whether the density is correctly specified, then we can take this sequence of the PITs and evaluate whether it's uniform. Okay? So that's what we will do. As a parenthesis, there are other properties that the PIT should satisfy, such as independence and identical distribution. And this is, if you're interested, because you could have a sequence where you have a bunch of 0 and 1s all happening unconditionally with the same probability, but it might be that initially you have a bunch of small values, and then as the sample goes on, you have a bunch of high values, right? So this will still tell you that the predictive density may be misspecified because in some part of the sample you're not doing quite right, in some other part of the sample you're doing not quite right, but then on average you're somehow hitting the target, right? So these are two other properties that we will not investigate here, but we have investigated with Tatevik in other works. Okay. So I will concentrate on testing whether the PITs are uniform. And this was done by Diebold, Gunther, and Tai. These are a bunch of very smart people. And so what you do is you plot the empirical distribution function of the PIT, and then you look at whether it looks like a uniform, right? So this would be the uniform distribution. Now, the issue is that there is sampling errors in the data, right? So how do you know whether this is indeed a uniform distribution, how different it is from this red line? And this is really what we want to do. We want to assess whether you are inside some confidence interval such that your distribution is uniform. Okay. Now, turned out that the approach in Diebold, Gunther, and Tai, this pioneering approach on evaluating the PITs, has some limitations, which is something that we want to tackle. One is that they ignore parameter estimation error. So what they do is that they take the sequence of the pits. So we had the pit, which is zt plus h, which is my integral of the predictive density phi t plus h from, let's say, minus infinity to the realization. Okay? But these predictive densities end up depending on parameters that are estimated from a model. Right? So Diebold, Gunther, and Tai take these as data, and then they plot this histogram and do their analysis without realizing that these are function of estimated parameters. And as you know, a function of estimated parameters will have a variability, will have a sampling variability that is very different from the case where you had known parameters. Right? So we need to take somehow that into account. And also Diebold, Gunther, and Tai did not take into account dynamic misspecification, and we also want to tackle that. So we're not the first ones to think about these issues, and Corradi and Swanson have done that. And for example, Corradi and Swanson have tested whether the pit is uniform. So they have tested whether this sequence of your pits is uniform when it is evaluated at the pseudo-true parameter value. So their null will be based on the parameter that is the limiting value of your estimated parameter. This will hold when the sample size is very large. Right? So, and the way they test this null of uniformity is the following. Rather than, so I don't want to scare people. I will show you later this. Okay. So the way they do this is the following. So Diebold would plot the empirical distribution function and test whether it's a uniform between 0 and 1. Okay, so this would be, if you will, the PDF of the pits. Corradi and Swanson look at the CDF. So the CDF of the uniform will be the 45-degree line between 0 and 1. Okay, so they will test whether, when they look at the cumulative distribution function, it's very different from the 45-degree line. So I wish I had two colors, but imagine that this is the estimated cumulative distribution of the pits. Well, then they will evaluate whether the distance between the cumulative distribution of the pits and the 45-degree line, the uniform distribution, whether this distance is large enough. Okay? So, and this is what the math on the slide was telling you. Okay, so imagine we call this axis R between 0 and 1. Then what they do is that they compare R, the 45-degree line, with the empirical cumulative distribution function, which is what you would have here. When this distance is large, then you reject the null. Okay? So this quantity here would be a measure of how distant the empirical cumulative distribution function and the 45-degree line are for every little r value. Okay? So Corradi and Swanson then say, look, let me take the largest distance. So the largest value here, imagine this is the largest value in absolute value. They would take that quantity. And they would try to, for example, here, they would try to see whether this quantity is very big. If it is small, then the null holds. If this quantity is very big, you reject the null. And the question is, how do we know how big this difference is, how different from 0 it is? Okay. So Corradi and Swanson have looked at this problem, have found that this distance converges to some Gaussian process and has some variance. And this variance is kind of complicated. Okay, so this variance looks like this, right? Why is that? Well, I mean, it's complicated because, just to give you some intuition, phi of beta hat can be thought of as phi of beta naught plus I take the derivative of phi with respect to beta times beta hat minus beta naught. So the distribution will have a component which is parameter estimation error that complicates things. So if you try to get these things in a reasonable model, for example, in a DSG model, this is pretty hard to do. Okay? It's true that they have a bootstrap technique to implement it, but that's what we try to do. You know, initially, we wanted to evaluate whether the DSG model forecast densities were correctly specified. That was our empirical goal. And then we were trying to implement this, and this turned out to be pretty complicated. So then we said, okay, why don't we take a step back and we think about a different way to implement this approach. And that's what we decided to do. We tested the null, not the pseudo-true parameter value. We are not interested in this quantity here. We will take this as the object of investigation. Okay? So we will not have to worry about this part here. We will take this object as the primitive data. So in a way, we go back to Diebold, Gunther, and Tai, which treat this as data, and this turns out to simplify your analysis a lot. So how do we end up doing that? So the trick that we use is that we will produce a density forecast based on a finite window of estimated parameters. So the parameters will be estimated on a sample of R observations, the last past R observations, and this will turn out to be very convenient for us. So we will test the null that the pit evaluated at these estimated parameters that come from this sequence of our observation, whether this quantity is correctly specified, And for us, what we will do is we will base our analysis on the same test as Corradi and Swanson. So we will look at the empirical distribution of the pits, and this should be uniform under the null. So we will compare it with the 45-degree line, the same test statistic as I showed you before. But because we have a different null hypothesis, then the distribution of this object will be different. It will ignore this part, and it will be much simpler. So in particular, this way of approaching the problem based on a window of estimation of finite size goes back to Amisano and Giacomini, who have taken a similar approach for forecast densities. So what they did is that they used this approach to compare forecast densities. We instead use it to evaluate whether the predictive densities are correctly specified. It's a very different approach. It's based on the pits. So, but the idea goes back to this paper too. And so how do you maintain this parameter estimated under the null? Okay, what is really the key to our procedure? So this could be a little bit abstract, but what it says is that if the window for estimation is finite, and if the data are mixing, then whatever function you're using, your function of mixing data, remains mixing. So then I can treat this as data and then implement my test, and the test will be correctly sized. Okay? So then our trick will be that the window to estimate this parameter is finite, and therefore this can be treated as real data, so that you don't have to have all this additional machinery of correcting for parameter estimation error. Okay? So this, if you will, is both the advantage and the limitation of the approach. It has to be implemented in rolling windows of finite size. Okay. So then I have an example, but I will not have time to talk to you about the example. You can read that in the paper. The interesting advantage of taking this approach is that if we assume that you care about parameter estimation error in this particular way, and if the model are correctly dynamically specified, you remember from the beginning we were trying to tackle two issues. One was parameter estimation error, the other was dynamic misspecification of the model. So let's say that we tackle only one at a time, so we tackle parameter estimation error, but the models are still dynamically correctly specified. So in that case, the beauty of the approach is that we can show that the pits is not only IID and uniform, but also that the sequence of these distances here, converges to a normal distribution with a variance that does not depend on parameters, okay, on nuisance parameters. So that means that each one of you can use different data sets, come up with different predictive densities, but then all of you will be able to use the same critical values which I can give you. Okay, which makes your evaluation much easier, rather than having to simulate the critical values or tailor them to your empirical application like you would do in the other analysis. Okay? So this is really the computational advantage that we get out of the approach. So what we propose to do is, so Corradi-Swanson would look at this distance and see if this is big enough. We're doing something similar. We're looking at that distance. Rather than in absolute value, we square it. This is for historical reasons. When we came up with this, we didn't know about the Corradi-Swanson, so we squared it rather than taking absolute values. But it's exactly the same, right? They are one-to-one mapping. So we take this distance and we square it, and then we take the largest deviation. And we test whether this largest deviation is sufficiently different from 0. So that would be one approach that we recommend. It is similar, if you know about density evaluation, it's similar to a Kolmogorov test, where you take the largest distance between your distribution and the null. Okay? Now, people could say, well, why do you take the largest distance? Maybe what you want is to give weight also to the other observations. And so another way in which you could measure distance is by the average of all of these deviations. So you take the area between this line, the estimated line, and the null. Okay, so you could take the average of them rather than the largest value. And this is known in the literature as a Kramer-von Mises type of test. So you can do either of them. And as I said, the computational advantage is that we can give you critical values to test the null of correct specification that will be the same no matter which application you're looking at. Okay? So let me give you a little bit of an example of how you could do this. Okay? So these are probably the only 2 minutes that are important in this talk. So let's forget about all the mechanical and all the assumptions and everything. You want to test whether your predictive density is correctly specified, right? So you get your predictive density, you evaluate it at the estimated, at the realized value, you get a sequence of these areas, which are the pits. And then you test whether these pits are uniformly distributed by looking at their empirical distribution function and checking whether it's different from the null. So these are the critical values we would give you, but what you would do in practice is you would get your empirical cumulative distribution function of the pit. That's the blue line, right? So physically what you will do is you will take this sequence and get, the cumulative distribution function. As easy as that. So that's what you will get. And then this would be the 45-degree line. That's the cumulative distribution function of the uniform. And you're testing whether this is different from that. So the Kolmogorov test would say, well, let's look at the largest deviation, and then let's see if this distance is large enough. And we give you these critical bands with these critical values where you can say, well, if this is outside, we reject. If this is inside the bands, we do not reject. So when we do not reject, then the predictive density is good. Okay? So this would be, for example, the critical values that are in the paper. You can test for the whole predictive distribution with the SOUP test or the Kramer-von Mises test, or you can look at particular parts of the distribution. Maybe you're interested in the lower tail, so we give you these critical values. The visual analysis is very interesting because it tells you when you reject, it tells you where is the problem. So maybe the rejection is coming from this side, or maybe the rejection is coming from this side. So if it is coming from this side, that means that you have, this will tell you where the misspecification is coming from. Okay. So let me move quickly to the empirical application. When the model is dynamically misspecified, we also tell you how to implement the test. It will not be based on critical values that we can tabulate, but we can give you Monte Carlo codes. If you're familiar with MATLAB, we give you Monte Carlo codes where you can get the critical values. Okay. So I'll skip the Monte Carlo analysis and show you just what you can learn from these techniques in practice. So in the interest of time, I probably have maybe 5 minutes. So let me just focus maybe on one empirical application. This would be the survey of professional forecasters, a data set collected by the Philadelphia Fed. And they give you histograms such as these, right? So, or this would be the pit, sorry. They will give you empirical distribution functions for each of the forecaster, we will take the average of these empirical distribution function from each forecaster. So we will get an average measure of uncertainty, of density coming from each of the forecasters. And then we will smooth it. We will smooth it a little bit so that we can use it as a continuum. Okay? So we will look at both GDP growth, which is output, and inflation. Okay? The definition of collected by the Philadelphia Fed has changed from GNP to GDP. We will just treat it, we just use the data as they are. So we will get these data. The data go up until, 2011. There's a typo here. We have revised the paper. And we will evaluate whether they are correctly specified. So here is the table with the results. And the results, unfortunately, are not particularly good. Okay? And so you can look at output, forecast densities for output, or forecast densities for inflation. These forecast horizon could be the nowcast or the 1 quarter ahead. Okay? And this would be the SUP type test, and this would be the average type test. So stars and daggers mean that you rejected the null of correct specification. Stars for the dynamically correctly specified test, daggers for the other one. And the picture here is unfortunate in the sense that clearly the predictive densities for inflation show a lot of misspecification. The predictive densities for GDP growth are misspecified for the nowcast, but sort of correctly specified for the 1 quarter ahead. So these are the only ones that survive to our test. So maybe by looking at the pictures, we can learn a little bit more. This would be density forecast for GDP growth. This would be the cumulative empirical distribution function of the pit, right? We are trying to test whether it's different from the 45-degree line, from the uniform, and these are the confidence bands. So clearly there are rejections here. There are too few values in this area than what you should have observed. So that means that there are too few values here than the actual realization, right? So that means that that's a problem in the data, right? So we would reject the correct specification. Here, for the 1 quarter ahead, we do not reject. These are sort of mild misspecification at the 5%. So maybe you should not be worried too much about that. But for inflation, there is a big misspecification, right? So clearly the information is off. Okay, so we hope that these techniques might be helpful for economists to improve their predictive densities. Another application is for the DSG models. So we've taken the DSG models, and for example, this would be prediction for output and prediction for inflation coming from a DSG model. We find a little bit of misspecification for output and no misspecification for inflation. Okay? Now, however, you should be careful to say that, you should not be saying that the DSG model has a better forecasting performance than the survey of professional forecasters. The reason is that the DSG model sort of relies on choices of prior, on the parameters, relies on the trending and so on and so forth, which are made on the full sample. So somehow there is a look ahead, there could be a look ahead bias here. This exercise was not done in real time, right? Although the forecasts are done in real time, the detrending was not due to the way in which this was actually estimated. So you should not interpret this as saying that the DSG model is suddenly a great tool and the SPF is not providing good density forecast. Rather than this is, we should evaluate the performance of the DSG model in real time. So I think my time is well off. Let me conclude. So we have tried to propose new techniques to evaluate the predictive densities to see whether they are correctly specified. So this is very different from the horse races, trying to figure out which one among the two of the predictive densities is better specified or closer to the truth. It could be that one is closer to the truth, but that one still is misspecified, right? So you want to evaluate that. So we have techniques that do that. The advantage is that they rely on estimated parameters, on a null on the estimated parameters, which we feel that is the way that the forecaster would like to evaluate their predictive densities. And they are nuisance parameter free in the limit, so we can give you critical values. and we have tried to show the empirical usefulness of these techniques in 2 empirical applications. Okay. So I'll stop here, and then I will let my discussant complain.